你听到我吗？你听得到吗？
我显示你正在讲话呀。
对呀、是你能听得到我？
你再说一下。
你好，
我戴个耳机啊，我手边有好。你说。
喂，听到我吗？
可以可以啊。
等一下，这也可以那个做这个视频或者是叫什么？
你是摁了那个解除静音吗？
我摁了这个 microphone，我现在想摁这个，你可以试下摁这个，摁这个，摁这个，摁这个 microphone，为什么又不行了
我不转了，我怕别人看到我的大脸。
？OK。
cho mình nhìn ngoài xem. Hello. I think this is the first online lecture for mechanical 59 okay, our main course. So first I want to let you know that yeah, I think according to our UST policy, so that we will change our online lecture into the thing, and then so that I want to make sure that you I don't know if you have you know how to use Zoom. This is something I think it's not very difficult, but make sure that you know how to use this kind of Zoom. Right? If you have some question, you can try to send a message through the chat room. Right? If you have some question, I think it would be better you try to. If you have some question, please try to send your question via this chat room. Okay, that would be better. Okay, and so that today I think I will try to give you some like tutorial about Arduino first, because I know that all you are working on your project, and of course unfortunately we do have this kind of a disruption about our this kind of a face-to-face lecture, and then if you have some problem for your project, you can try to send me a message, or you try to okay, so you can try to put some question on our Canvas website. Okay, so that let me see. Let me check. Resume sharing. Okay, so that if any question, please try to ask. Right? Don't be afraid, because I think we run out of time. So that again, so today I show you one of quite important this kind of a project, right? This is a 7-segment display, and we ever talk about several projects, right? Arduino tutorial first is temperature sensor, LN35 temperature sensor, and then we talk about the photo cell light sensor, and then we also talk about LCD, right? Today we try to show you about one of also important component we call the 7-second display. Sometimes we call SSD. Okay, so that of course here I just give you some brief introduction. So basically, now most likely you have experience to use temperature sensor, light sensor, and also we also have a temperature humidity sensor and air quality sensor, right? And this sensor can connect to Arduino, right? And Arduino has this board has ADC, and then in this case, your MCU can get data, and how you send the data to your computer over the display, right? So this become very important. LCD or LED or 7-second display, right? Why this is a 7-second display is so important, because I think in your daily life you can see we have so many different kind of LED display in LED watches, and also some of industrial like machines. You also have this LED display. In your Arduino kit, you basically you have not only have a several LED display. Okay, so basically what do we have in your Arduino? You have this kind of a LED display. This is a 1-digit LED display. Oh no, so sorry. Let me show you here. I already tried to connect. This is a 1-digit, right? 7-second display, and then also we have this is 4-digit in your Arduino kit. You have 4-digit the second display, and also you also have this one. This is an 8x8 dot matrix LED display. Okay, so these are today I just show you some very simple like introduction of these display. That means basically how can we identify this kind of 7, actually it's 7 plus 1, or total is 8 actually. This kind of 7-second display is actually is a figure 8 grouping of LED. Here you can see 8, right? we actually put this kind of a spatial coding, right? That means on top we have A, this LED, the net A, and then right hand side we have B, and then C, D, E, F, G, and then we have one more, right? This is 1, 2, 3, 4, 5, 6, 7, and plot additional decimal place, right? So actually in reality, actually we have a 7 plus 1, we have 8, okay, segment actually, okay. And in general, we have 2 type of this LED display. We call the common cathode. That means all LED cathode are connected, and the second one is common anode. All LED anode here will be connected. So that, how about for your Arduino kit? What kind of product do you have? Do you have any idea? Well, you can look at some additional data sheet, then you have more idea how it's. Anyway, here I just show you about why this is useful, because you see, with this kind of 7 segment, we can really display a lot different kind of information, right? From our sensor data, we can have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Or sometimes we also have A, B, C, D. Some alphabet can be able to show. So this is very useful, right? And then you see, we can really have all the decimal digit 0 to 9, and also selective this alphabet character, right? A, B, C, D, E, F, G, right? So this will be possible, right? And this become very useful, right? For you, once your sensor data, how you can use this kind of SSD to show your sensor data. That's a very important thing. And then, of course, we also have not only show the static information, we also have some blinking, right? Like blinking of this kind of like a digit, right? A number. So this is also possible. And then, of course, again, I show you, basically we have this two type of 7-second display chip. Basically, common cathode and common anode. Okay, and so what's the difference between these two? Basically, common cathode, you see here for number this A, right? LED, right? So basically we can provide the maybe VCC 5 volt, right, from Arduino output, digital output, and then here one is positive side from LED, another is negative side. Okay, you see this negative side, the terminal of the LED will be connected all the way to the grounded, this terminal, right? So that is so this A is positive side with anode, right, and negative side with cathode, right? The same thing for B LED. We also have positive connect to Arduino the digital output, and negative one with cathode side we will connect to our common ground. You see, common ground. Let me try to do annotation. Let me see. Well, this Zoom has some way I can try to highlight. Let me show highlight. Basically, you see, we have this is the cathode, right? And then here we can connect all the way. This is grounded, right? So that's why it's common cathode. Okay, let me change the color. So okay, so that again, so this is the type of thing, right? And second type basically is with common anode, right? That means anode means positive side here, right? For A LED. So the positive side connect to the VCC. Oh no, sorry. This A terminal, right? So that connect to this negative, okay, anode side, and then positive will connect to this VCC. Right? The same thing for the B LED. We see the negative side will connect to this kind of B terminal, and the positive, right, will be connect to here. See, from here, VCC, right? So that means positive, negative, right? So in this case, we can see the same thing for here. We also have this kind of a anode. This is anode and this anode. That's why we can call this common, right? This the positive side and negative side, right? So this is the two different type of 7-second display. Okay, and then okay, let me go to the next one. So how can we operate this LED? I think we'll describe this one before. Right? Basically, is we try to have a two-terminal LED is a two-terminal device, positive anode, negative cathode, right? So that if apply the VCC, 5 volt on this positive side terminal, and then a negative one we connect to the not any grounded. Most likely, if you apply there's a high voltage on LED, and what happens? Typically, we have seen the typical behavior LED, right? For this is V. For the typical LED, so X is VD and Y is current through the current. Now see, so in general, we have this kind of nonlinear behavior. So if we apply the voltage, right, for example, 5 volt to this kind of LED, and what happens? So that in this case, very possible if the voltage is much bigger than the threshold voltage, VT, the threshold voltage, and then you turn on LED. But if your voltage too high, what happens? What do you think? If voltage high, you can see this is exponential function, and what happened? Actually, it's very possible it may burn your LED. This is very common. So that so in this case, to make our LED work properly without damaging, right? Using an LED to LCD, LED connect to Arduino MCU. In this case, we have to make sure that we control this current to certain regime. Okay, we cannot let this current too high. Otherwise, you burn LED, right? So how can we do that? Huh? Basically, we have a way. How can we try to control this kind of LED to prevent this kind of problem? Do you have any idea? Huh? Basically, one simple way is we try to put one resistor. If you put one resistor in series of LED, and then in this, it can control this kind of a current to be smaller, right? So that is something become very important. Okay, now let me try to look here. So here, let me show you here. So that let me show you how we can try to look at the typical operation of LED, right? So that you see for this particular one, basically we have a LED connect in series with one resistor. Typically, we can show you if you have 220 ohm. Actually, this is very common in your Arduino kit. We do have this now LED the resistor, which is 220 ohm. Okay, so if you connect LED to a resistor and then apply 5 volt on one side, the positive side, and negative side of the terminal of LED connect grounded. In this case, what happened? Huh? So in this case, we can try to do some simple calculation. Right? If you turn on, turn off this 5 volt, and then actually if turn on this 5 volt here, this switch, right? So that you see, then we can turn on LED. If you turn off this kind of it grounded, so that in this case, you see both sides of this LED terminal is grounded. So that in this case, we have no the light from our LED, right? So that's basic thing, right? So that means that you can do some simple switching. So how can we do the switching with our Arduino? Well, you can use manually, right? You have some mechanical switch. We do have some mechanical switch in your Arduino kit, right? So that if you have this mechanical switch, of course, you can push a button and then turn on, turn off, right? Your Arduino, right? So that you do have this kind of mechanical switch. But of course, that is not good, right? If you want to automatically to show some information, so that probably you don't want to use a mechanical switch, right? So you want what? Use Arduino, right? The digital I/O, the output, to provide this kind of 0 to 5 volt, right? So it can turn on, turn LED, right? So that is a basic way we can use this one, okay? So of course, we are not only control one LED, or control, it's in general 7-second display, right? In this case, how can we do that? That means you need to provide a series of a connection between this kind of LED 7-second display to Arduino with additional this kind of resistor. So here I show you how we do that. For example, for one digit, the 7-second display, right? You can see A, B, we call it A, B, C, D, E, F, G, right? And then each LED we will in series connect with one resistor, right? So that in this case, we'll provide 5 volt from Arduino MCU, right? And then you see 5 connect to here, and then of course we have also a common. We have a common here. You see, actually there's one common we call the here, right? So that in this case, if you connect in this way, what do you see? What kind of output we have? A connect to, maybe I change color. A connect to here 5 volt. B or 5 volt. C is a 5 volt, right? And then D, you see, actually, oh, we'll be careful. Oh, we have this one 5, 5, and this is 5, 5, and C will be connected here. Okay, so this is grounded. And how about E? A, B, C, D. D is 5 volt. And then our E is 5 volt. And then F, grounded. So in this case, with this kind of connection between 5 and grounded, right? And what kind of information do you have? I want to ask you, huh? Do you have any idea? What kind of output do you expect? Huh? What kind of output do you get from for this particular connection? Any idea? Well, so that you need to go back to our previous slide. If you go back to our previous slide and then you look at here, A, B, C, D, E, F, right? So that you have to understand about this kind of connection, and then to see how. Let me try it here. This one should be copied to this side. Display here. See? So A is 5, B 5, right? And C here is grounded. So that you look here, A is on, so that actually we can do one by one. That means, for example, if it's common cathode, that means A is on. Let me see. So you look at this kind of configuration, and then you find the way how can we see the real output. See? So 5 volt, A, B, D, E, G, and grounded EF. In this case, we can show actually our output is 2. Okay, so this is now the way I think you can try to think about how we can use this kind of 7-second display to show some information from our sensor. Okay, so this is something, it's not very difficult, but it takes some time. And then of course, again, how we pick and write this kind of resistor for our LED in this SSD. So as I told you, LED is nonlinear behavior. So you have to have additional resistor. Its behavior is here nonlinear. Okay, so we have a VD and ID, right? Nonlinear, so that if you don't add additional resistor in series of our this LED with our resistor, then you will burn your LED. Okay, so this is a common. So that this is it. And of course, we need to find some balance, right? If resistor too large, what happens? Then your current very small, and your LED output light will be very light intensity very small, right? So that you need to find some balance, right? Make sure the resistor is the value, it should be optimized. So what's the typical resistor we need to use? Actually, you also have to look at the data sheet. So that so for example, for the one in your Arduino kit, let me see if I can open this kind of let me try to show you. I don't know if, did you see this kind of see? Basically, this is a data sheet of 7-second LED display. Okay, you have a 5611A and B. So what it means? Arduino kit, we have this kind of code 5611A common cathode, you see? And then if you 5611B is common cathode. So this can tell you about one thing. Our sharing is stopped. Let me see, how can I? Let me see. Sorry, I need to think about how to use sharing. Sorry. Sorry, let me try to share my screen. Let me see, how can I? Sorry. Hello, can you see this kind of our new this is a Arduino 7-second display data sheet. Can you see this kind of data sheet? Basically, at least for typical data sheet, you see they show you about all the specification, and then also they show you this kind of common cathode. Okay, and then they tell you about typical current. You see 20 milliamp, and then I tell you about the typical intensity for per segment MCD. Okay, this is a light intensity unit, right? From 9 to 12 MCD. So that if you use 20 milliamp, then your typical output intensity here. They show you typical VF, the full voltage. That means that the current, right? The typical current is 20 and the voltage about 2 or something. It really depends on different kind of LED. Okay. Let me show you. Stop sharing. Let me. Anyway, so here I show you. Basically, you need to pick pick a reasonable, this kind of resistor, then you can make sure you're seeing. So here I do some simple calculation for you. Basically, if you have typical Arduino, right, will provide this kind of 5-volt signal for Arduino. Let me show you, right? So typical voltage, from Arduino is 5-volt, right? And then so that we need to find some typical R value, right? And then typical voltage across LED is 1.5 volt, right? Based on the basic electronic the circuit theory, Kirchhoff's voltage law, KVL, so that you see 5 volt on right hand side, and then here is about this voltage drop here is about 1.5, right? So here, this voltage, that means this is positive, this is negative, and then the voltage here is 1.5 volt. Okay, so in this case, I can easily try to see. You see, 5 minus 1.5, right, is 3.5 here. So that this is for resistor, right? Now on the right hand side, this is 3.5 volt, and then the left hand side, this is 0. This is 0, right? In this case, I can calculate. This is for based on the Ohm's law, right? V equals IR, right? The voltage across the resistor equals current multiplied by the resistor. So that in this case, 3.5 minus 0 divided by resistor here equals current. Or if we pick up typical current, as I show you in the data sheet of this LED and 7-second display, so it's around 10 milliohm, right? So over 20 milliohm. So here, if you try to estimate our current, it's probably 20 milliamp, right? Maybe 10 to 20. In this case, then we can have some idea about what's the typical value we need to use, right? So here, you see, so that in this case, based on this kind of typical 10 to 20 milliamp, so that we can find our resistor value should be about 233 ohm. Okay, so you pick up this kind of resistor, and for the Arduino kit, you have actually you have a standard. This kind of a resistor value is 220 ohm, or this is close standard value in your Arduino kit resistor. So that this is something that you can use this one to build this kind of Arduino with this 7-second display with LED to make it work. Okay. Here I just show you some a connection. Right. So basically, you need to remember you connect this kind of A, B, C, D, E, F. So I need to click here, right? And then so let me show you again. You do need to have connect this kind of each pin 1 to Arduino pin A, our SSD pin 2, Arduino pin 7, and then so I do a series connection, and then also you try to have some program, right? So here this is very simple program. So how we can control so many LED, right? It's 7 segments, 7 plus 1, total is 8, right? So that 0, 1, 2, 3, 4, 5, 6, 7, 8. So basically we define a matrix in Arduino program. That means 7 SEG digit actually is array, right? 7, first one is 0 to 9, so you have the 10. Right? 7, that means we talk about 7, that means we have 7 LED, right? So in this case, 1, 2, 3, 4, 5, 6, 7, right? So that's why you see we have this kind of matrix, right? So this is here we have a 7, and here total of 10. So that's why you 10, 7, right? So the 10 by 7. So you define a matrix, and then why we need to have this kind of array, because we can easily try to use this one to assign this kind of 1, 0 turn on, turn off LED, right? With this kind of simple definition of array. So this is provide a simple way to control this kind of 7-second display. Doing that, this is something quite important, right? Once you have an array of this kind of LED, you need to think about how we do the simple control, how to write the program. Okay. Do you have any question for this particular one? And then, of course, here we try to using right. We set up this thing. Basically, we define the LED, the Arduino output. Okay. Basically, Arduino here we have a digital output, and then make sure that the pin 2, 3, 4, 5, 6, 7, 8, 9 to be output. And then in this case, we try to write that 0. Okay. So anyway, so here this is the way we try to make sure we try to send our binary output, right? 0, 1. I mean 0 is grounded, 1 is 5 volt, right? To our LED. And then write that here. You see, we can try to control this kind of digital write for our this kind of LED display. Then here, so we define this kind of additional subroutine, 7-second write, and then input one input parameter digit. This digit means because for our LED, right, we want to output 1. This is, we have this kind of from the digit, I mean from 0 to 1, 2, 3, 4, 5, 6, 7, 9, right? So that in this case, and then 4 of this by segment, a sec count, right? That means from 0 and then gradually increase 1, 2, 3, 4, 5, right? And this is right. So that I try to assess. Now you can see, I try to assess this array digit. This here segment count, and in this case, I try to continue to provide this kind of output digital write from this kind of the message here, right? And then go this kind of pin, right? Doing that. So here we define the pin is 2, and then this is a subroutine we use, and then we use this is the main program. So that the main loop, that means we try to have this kind of for loop count equals 10, and then gradually decrease 10, 9, 8, 1, and then delay for 1000, and then try to provide this kind of a count. 10 minus 1 is 9, and then in this case, I can try to use this subroutine to continue to set this kind of information, right? Using array information, and then delay 4000, this kind of I say milliseconds. So this is the way we easily try to show you how we can have this. First is hardware connection, and then use subroutine to provide this kind of a program to control send out signal. Here I show you basically if you try to run the program. Actually I do have this thing. Let me show you about Arduino program. Okay, here this is the Arduino program. Basically, I don't know if you see. Okay, so that of course the same thing. You have this Arduino program, and then you try to compile. Put this here, compiling, and then uploading to see, and then of course you have to make sure you have the right connection, right? And then here I show you. I think I made some little mistake. I think my connection have something wrong, so it's not exactly 0, 1, 2, 7. Anyway, so that again they have so many wiring, right? So that if you make some mistake in this thing, then you also have a little problem. But anyway, at least I can show you at least this program it can work, and then you upload this program to this Arduino. Okay, so then I think you can play this kind of Arduino thing. I don't know, do you have any question for this example? Of course, again, this you can try to use not only one digit. You say we have actually have a 4-digit or 8x8. Okay, 8x8. This LED display. You can really play a lot to now use this one for seeing. You see, this is something we have many different things. Okay, okay. So I don't know. Do you have any question for this particular Arduino tutorial? Any question? Huh? Because I told you, we have limited time. I don't think I can show you all the component. We have more than 30 components, but I believe this component SSD is very useful and important. So that's why I hope that I will describe this one and make sure that you know how to use this one. No, huh? Do you have any question for this particular thing? If not, then we will try to give you some additional information. LED is very, very useful. Okay, LED is very useful so that how we have this thing. So there's a new generation of LED, micro LED. It turns out, so the one you have in Arduino kit, well, we can call it a macro LED. You have a much bigger device, and okay, this LED is based on 3-5 semiconductor. It's not this silicon based, right? Because you need to have this kind of optoelectronic output, right? This transducer, so that this is, and then so micro LED is a new technology, and what's special thing? Basically, micro LED has micro, right? Typical size LED, micro LED is around less than 100 micron. Okay, and then so that we still have to do some microfabrication process based on our we described in our lecture before, right? As I show you, we have no matter how complicated your IC, semiconductor device, main sensor, we have what? Patterning, right? Etching, deposition, and doping. And then we can make this kind of array of this LED, and then we do what? And then once this thing, and then we try to make this kind of LED on the wafer. We call it AP wafer, right? And then try to do dicing, right? Sometimes called dicing, sometimes chip singulation. And then we try to do what? Pick and place for each small micro LED, and then we try to pick and place, and then try to put in a magic form. Okay, so this is the way. And then in this case, again, this kind of micro LED has interesting performance, right? In our previous Arduino tutorial, we talked about LCD display, right? LCD display has some problem, as mentioned before. What's the problem of LCD display? Huh? In Arduino kit. Basically, it's very power hungry. Where backlight or backlight illuminate, right? This kind of liquid crystal, right? So in this case, we consume a lot of power. Okay, so this is very old technology, but it's not good, right? So in our previous lecture, we talked about OLED. New smartphone, right? For example, iPhone 10, there's not LCD display. It's too power. We want to have a low power, right? Consumption. So in your like iPhone 10, actually it's using OLED, okay, organic LED, because we don't use backlight, okay, for like LCD display, and we save a lot of kind of energy, right? So that and then of course micro LED actually has even better performance, and you can also set power, and also performance actually even better, right? So that now in energy, gradually people want to use micro LED for big LCD TV or for smart watches. So that is ongoing. This R&D, and people make a real product. Okay, so this is something. Let me quickly show you the history of this micro LED. First developed by Professor Jiang and Professor Lin of Texas Tech University, and then when they were still at the KSU about year 2000, and then gradually people try to work on LED, micro LED, and then around year 2012, Sony demonstrated first micro LED TV, right? They called the crystal LED, and of course at the same time Samsung also tried to also work on micro LED, and so that actually Apple also think micro LED is very important. Okay, so that people, I don't know if you have seen this Apple Watch. Actually, they use micro LED because you can save a lot more power. Okay, so this is, and then here I show you one interesting my own experience. So like Apple acquire one micro LED stock company, LuxView, in about 5 years ago. So that the LuxView technology company, the stock company based in Silicon Valley and also in Hsinchu, in Taiwan. Hsinchu is Taiwan's second valley, I would say. TSMC, UMC, there's so many this kind of semiconductor company in Hsinchu, Taiwan. And then, so that this company, LuxView, raised about $43 million from several VC, also from MediaTek. MediaTek is one of #1 IC design company in Taiwan, and they used to make this kind of the processor for this kind of mobile phone in mainland China, right? And then gradually also Himax is another company in Taiwan. They so that provide funding for the thing. Then Edward, well, my UCLA mate, he used to work for several men's company, U Machine, and men's style company, and Withdrawn. And then he was the director of operation for this micro LED sub company. And then, and you see, you can look here, they do have a series of patents from this company. And then eventually they Apple acquire this company in 2014. Okay, and actually many big company actually put a lot of money now in this micro LED. Samsung, a huge amount of money, and Foxconn is only do assembly of iPhone, iPad, or Mac. Right? They also try to work. They put a lot of money in micro LED company. These company, AOT, LED, MarkTech, are the company invested by the Foxconn, very good. Okay, and also USD. We also Professor Amy Lau. We also I don't know. Excuse me. I need to teach you now. Okay. Anyway, so here I just show you. We have also Professor Amy Lau in our EC department, also do this micro LED research. And so of course, at this moment, I see this micro LED are still. I think people continue to work on micro LED. So not only smart watches, I can see in the near future, people think many of this kind of mobile devices, smartphone, smartwatch, and maybe some additional like VR, AR, okay, MR, so that device, wearable device will use this kind of micro LED because it can be low power. And performance-wise, it's good. Let me show you the comparison about this three technology. LCD, right? And again, you need a big light. The constant ratio is 5001, and then the response time very slow, millisecond, right? And then power consumption is very high, okay? And if you, for your Arduino this LCD display, if you use this battery, probably can only last for, I think, not a short period of time. So then, that's why, like many of smartphone company like Apple, they iPhone 10 actually they use all LED, cell illumination. And in this case, now it can mean power consumption will be medium, and then so that is the contrast was good. You see, it's used for wearable and VR. Okay, so the resolution is good, right? So micro LED, why is important? Cell illumination. right? You don't need a backlight. And then constant ratio is good. Light time, long. Response time, nanosecond. Right? Cost, oh, it's still expensive. If you do mass production in the future, probably cheaper. And then power consumption, low. See, for all the mobile phone or wearable device, you need low power, this kind of, so in this case, so micro LED is much better than LCD and OLED. So that's why, so many big companies really put a lot of money, right, on this micro LED. Again, you see VR, so that the VR, virtual reality goggle, and AR, right? We also have the AR devices. All will be, most likely people will use this kind of micro LED for this kind of mobile devices. Okay. So here I just give you. I don't give any question for this particular tutorial. I think this is a quite useful information for you, right, to understand about this thing. Do you have any question for this particular tutorial? Again, I think you can try to any question, huh? Any question for about this particular tutorial? Any question? Okay. Anyway, as I said, this is just give you some idea. I hope that you can try to play about more Arduino kits. There are many different components. Of course, I will provide additional tutorial for you and put on our campus website. Okay, and so if not, and then I think I will go to another interesting topic. So today, I hope I can change gear to show something different. So that actually, in your campus website, actually you have this kind of SME, the handout. Let me share you about this thing. Okay, in your if you can accept this kind of campus website, you have you can look at this ASME video. This is a special ASME workshop about MEMS. Although it's very old, it's 1996, about the real like a product development about MEMS products, because we already talk about many different kind of topics, right? This fundamental thing, right, in terms of fabrication and the basic concept of MEMS devices, sensor, actuator. Today I want to give you watch this kind of video, and then so that you have more idea about this particular product design. Here, let me show you about. Let me share about this window. Sorry, I showed. Okay, here I want to give you this kind of watch this video.
Good morning. Welcome to ASME's 25th live interactive satellite broadcast. Sponsored by the Micromechanical Systems panel of ASME's Dynamic Systems and Control Division. Today's program is titled Microelectromechanical Systems, MEMS, Case Studies of Commercial Products. The program is televised from the ITV studio at the University of South Carolina in Columbia, South Carolina. My name is CJ Kim. I'm the chair of the ASME's Micromechanical Systems panel, and I'll be your moderator today. I'm a professor in the Mechanical and Aerospace Engineering Department of the University of California at Los Angeles, UCLA. I received my PhD in Mechanical Engineering from the University of California, Berkeley, with the study on MEMS. I joined UCLA in 1993 and have been teaching and doing research on MEMS since then. MEMS is an area attracting enormous interest throughout different disciplines in engineering and science, advancing with a tremendous speed these days. ASME televised a program on MEMS 4 years ago, introducing the technology. There are quite a few short courses offered in the States and other countries, as well as several formal courses and even degree programs in universities by a few, including myself. However, some of the common questions we have are, so what does this MEMS do? Or, that's great, but why don't I see the product in the market? Or, I have this great idea, how can I commercialize it? So today, we will try to answer some of these questions by showing examples. We have today 5 leading experts who will discuss not only the technology behind the products that have been developed, but also the economic advantages and limitations of using MEMS technologies from their own experience. Our presenters will describe the key MEMS devices that were successfully developed as commercial products, such as inkjet printers, airbag sensors, automobile fuel injectors, and pressure sensors. There are many products currently under development, but not hitting the market yet, due to the short history of the field of MEMS. I believe the commercial success of products like these today, in the meantime, will build confidence for further investments from both the government and the private sectors to sustain the growth of the field to the next level. This broadcast is live and interactive. We will have a question and answer period after each speaker, and also from 3:15 to 3:45 p.m. Eastern Time. We invite you to call or fax your questions in anytime during the broadcast. The toll-free number is 1-888-531-8685. I have to note that it is 888, not 8100, which is showing in your class note. The fax number is 803-777-6396. These numbers are also listed in your note. Again, the toll-free number is 888 and will be flashed on the screen periodically for your convenience. The number in your note is wrong. It is 888. There will be 2 breaks during the broadcast. 1 half-hour break from 12:35 to 1:05 p.m. Eastern Time, and a 10-minute break from 2:25 to 2:35 p.m. Eastern Time. 3 ASME videotapes will be played during these breaks for your information. During the first break, you will see Resource ASME and the Statue of Liberty. The other is Mothers of Invention, which will be played during the last 10-minute break. We also have a studio audience of local ASME members and other guests. I'd like to take this opportunity to welcome them, to invite them, and participate in the question and answer sessions. Our first speaker today is Dr. Richard S. Payne. Dr. Payne is the director of the MEMS Center at Analog Devices, Incorporated, Cambridge, Massachusetts site, where the first dedicated wafer fabrication line for surface micromachine devices has been built. He has worked for Analog Devices for 16 years and was at Bell Labs for 10 years before that. He's a fellow of the IEEE and the recipient of the prestigious 1992 J.J. Abrams Award. His presentation is titled The Development of MEMS Airbag Sensors. Rich?
Well, thank you, CJ, for inviting me here to talk about one of my favorite topics, that of the ADXL50. I'll give you a case history today that takes you through some of the motivations for the choices we made and some of the reasons why we made the choices we made, and maybe some of the economic factors and some of the developmental issues that we saw along the way. First, I'd probably like to tell you my definition, at least, of MEMS. MEMS are micro electromechanical systems, and coming from an electronics company to the ASME, I wanted to make sure you understood there were electronics in here too. I'll also stress the system aspect of MEMS quite a bit. They're typically involving a high degree of interaction with the real world. That is, they transduce signals from the real world, like mechanical, photonic, electronic, chemical, or fluidic signals or phenomena in the real world through a sensor of some sort into a core, which is really the intelligence of the MEMS system, a place where some signal processing or some control functions might be done on the signal. Following that, the signal would be transduced into some sort of actuation effect, in effect having an impact back on the real world. In some cases, in many cases, some of the early MEMS are purely electrical signals being generated to the outside world. In other cases, and some of the people that will discuss things later in the session, you'll see some fluidic and also other effects on the real world. When we initiated the development of this sensor back in the 1987-88 timeframe, there were several technology choices to be made. There are really various ways of implementing sensors and implementing microelectromechanical systems. In the first case, there was in existence a lot of devices made with bulk micromachining, that is micromachining into the bulk of the silicon, and also some studies on surface micromachining. So we had to choose between bulk and surface micromachining. In terms of the construction of the device, one is also often faced with a question of whether to hybridize the system, build it out of several pieces, and make it a hybrid construction, or attempt to put everything on a single chip. And the third choice one often needs to make, and one needed to make in the case of a motion sensing device, one which could sense airbag crashes which necessitated the deployment of airbags, is the particular transduction mechanism, whether one used piezoelectric or piezoresistive effects of the semiconductor device, or as was our choice, a capacitive sensing device. And I'm not sure you can see the colors terribly well, but at least the right-hand side shows things in green. The left-hand side shows things in red. Turns out part of my background that CJ didn't tell you about was that I went to Dartmouth College to get an undergraduate degree, and our color there is green, and our major rival was Harvard, whose color is crimson. So I always tend to use green for good and red for not so good. looking at that first choice, that of surface versus bulk micromachining, the very nature of surface micromachining is that it's surface, as its name might indicate. It's made with standard integrated circuit technology on the surface of a silicon wafer, which is almost always the substrate in surface micromachining. There are really two critical levels in the process that are characteristic of the micromachining. First is a sensor layer, which I've labeled here in green, which is a polysilicon layer, and designed in our case to, and in most surface micromachining, to provide the active element, the moving part, or the actuator in a MEMS system. It's usually been placed in the process on top of a sacrificial layer, which in the latter part of the process is etched away to leave a freestanding structure as part of the overall system. In bulk micromachining, silicon substrate is typically etched through from the back in most devices, leaving some sort of membrane structure. What I should point out, and what really determined, one of the main reasons in our choosing surface micromachining is that the characteristic dimensions of the surface micromachine devices are in the neighborhood of 1 to 2 microns. We used a 1.6 micron sacrificial oxide and a 2 micron thick sensor polysilicon layer. So in that the characteristic dimensions are on the order of 2 microns. Very small structures, structures of that order can be made, although larger structures as well can be made. In the case of bulk micromachining, one of the characteristic dimensions is the thickness of the silicon substrate, and typically 500 microns on the order of 0.5 millimeter is the characteristic dimension. So if you want to make small devices and you want to make integrated devices, as was our intent, the choice of surface micromachining was fairly natural. The next technology choice that needed to be made in the development of this particular device was whether to use a monolithic construction as shown on the left, where the sensor and the electronics were fabricated at the same time on the same piece of silicon, or a construction in which the device was built out of pieces, a hybrid construction, where the electronics might be on one piece and the sensing structure on a second piece. Now, I think this is pretty much a case of choose your poison. And I think there are pluses and minuses in both cases. In the case of our device, choosing a monolithic construction optimized the cost for us. In the case of some of our competitors in this field, the choice of a hybrid construction might optimize the choice for them. One of the things that's characteristic of sensors, and MEMS sensors are no different, is that some of the dominant costs end up in the back, what I'll call the back end of the process, the assembly and testing of the sensor. They're different than integrated circuits. Is one of the key differences, and hence the silicon costs are not in general the totally dominant cost element in the equation, and so you can live with, I would say, both kinds of constructions. And our choice, given the long-term system desires of the company and its business strategy, were to fabricate the device out of a monolithic construction. Well, having decided to essentially make a surface micromachine structure instead of a bulk structure, having also decided to use a monolithic construction as opposed to a hybrid construction, the choice of the particular sensing modality was very simple to make. In the case of silicon, there's really no viable piezoelectric effect. The piezoelectric effect in silicon is very small, and so to use a piezoelectric sensor in silicon would have amounted to introducing what I'd term a foreign material, something like PCT or zinc selenide or some other material that was not really compatible with the silicon processing, and especially not, which I'll get into a little bit later, not compatible with processing this material in a line in which many other integrated circuit devices were being manufactured. Another choice, and the one that had been made by the majority of people in the mid to late 80s when we started in this business, was a piezoresistive transduction mechanism. Piezoresistive effect in silicon was very well characterized and existed in many devices, but it has a characteristic temperature coefficient of resistors in silicon, which can be as large as 8,000 ppm per degree C. It is something which needs to be compensated for. So you start out with a transduction mechanism, which at the very beginning requires you to do some additional circuitry to compensate it. So what we chose was a capacitive transduction mechanism. Capacitor is inherently zero TC. First order, the dielectric constant of air or nitrogen, which is in most packages, varies by only 0.1% over a 200 degrees C temperature range. So that the fact that there was no temperature dependence was a very strong motivating factor for us to choose a capacitive transduction mechanism. Another thing, being part of an integrated circuit company, was that we had a lot of good circuits, and measuring changes in capacitance turns out to be a particular circuit technique which is fairly easy and very powerful. So in the end, again, we decided to use a capacitive technique instead of any of the other transduction mechanisms. So in summary about the choices, there were really, the choice of surface micromachining enables very small sensors whose characteristic dimensions are in the order of a few microns. It enables monolithic construction. The process integrates much more naturally into a single chip construction. Surface micromachining also works very well for capacitive-based sensors. So again, it fit with that overall scheme of things for both sensors, and less so for actuators. But so far, the device I'll talk about, and most of the devices that I'll show you examples of during this talk, have very little other than electronic actuation, sending out an electronic signal. Certainly for the future, there's a high level of integration enabled by surface micromachining. And really, there are many paths to the future that this technology can enable. I'll try to show you a few of those paths as the talk unfolds. Since what CJ had asked for was a case history, I figured I'd give you the case history fairly explicitly. This project really began with a sensor that was in manufacture in the early 80s at Analog Devices, which did very well. It was an integrated circuit temperature sensor. And at that point in time, in a variety of different groups, a market research group in Europe, and market research in the group that managed that sensor, they looked around for other things that might be done. So it was really a market-in project from the very beginning. Market-in being one where you ask the customers in the marketplace essentially what they want. By 1988, I became involved in the project, and it was formally, rather informally constituted. There were some other things that were formally started in 1988, but a group of people who were interested in trying to make an acceleration sensor got together. By 1989, those people had essentially abandoned what they were doing on other projects and became full-time involved in making an accelerometer, an airbag crash sensor. By 1990, in about a year, we had proven to ourselves that this whole project was feasible, but it took quite some time to develop a complete product and to convince several customers that it was worthwhile jumping to what was then a totally revolutionary technology. By 1991, early in 91, a very full function accelerometer, much like I think the picture I'll show you later has a mass date of 1991, and that was when the accelerometer itself was clearly demonstrated at the chip level. And at that point in time, giving something to sample customers, we developed 3 partners in the program, and we sampled parts to those programs in 91. And actually, in 1991 at Sensors Expo, we had a joint presentation with people from Berkeley that had been collaborators on our surface micromachining efforts, us having developed a component, and a systems manufacturer who had integrated it into a real product. It did take, 1992 is missing from this slide because it took a couple of years to really deal with all the issues associated with ramping from a feasibility demonstration, even though it was the final silicon, getting into a package and required additional time. By 1993, it was in production on Saab 900s at a fairly modest level. The part was sampled to the world in mid-93. By 94, and we had convinced the largest U.S. automotive manufacturer to use it on a select Buick Oldsmobile and Pontiacs. By 1995, an order of magnitude improvement had been realized. And by 1996, we see several million airbag crash sensors rapidly displacing mechanical components in cars around the world. Just a characteristic of the market that made this device especially attractive is that by 1994, there was nearly 100% penetration shown in green of mechanical airbag crash sensors into automobiles around the world. Either as a standard feature or an option, airbags are available on all 40 million automobiles. And the projection, given the fact that there's a significant cost savings going to a single point electronic accelerometer enabled system, is that by the year 2000, there would be a transition of these 40 million cars from mechanical switches to 60 to 70%, or 75% to 80% electronic, most of which we believe would be surface micromachine sensors, given the economics of the situation. So it was an excellent marketplace. And why is it that you actually need MEMS? Something we had to describe to our customers, and that is that motion is really required. You need a mechanical sensor. You need something more than electronics to make an airbag crash sensor. For our case, there was an IC line within the company. Analog Devices is at that point in time was about 500 million. There'll be $1.5 billion soon, and that was the environment in which and the constraints under which sort of we existed. And it was also a case that the circuit strengths within the company, the resources available to call upon, were there in terms of good, strong circuits capability within Analog Devices. So the very first system that we chose to implement was a very simple subset of that larger picture of MEMS that I showed. We like to refer to it as an acceleration to voltage converter. That is a system in which a monolithic chip transducts acceleration and outputs a simple voltage, which is proportional to acceleration, making it fairly simple for the user. Many of whom, in many of the systems applications that we were seeking besides airbag systems, are more mechanically oriented and want something that's very simple electronically. So we used a black box approach in the development in order to try to keep things simple. Quickly before I get into pictures of the accelerometer and the more complex system, I'd like to describe how the device really works. In this case, a polysilicon element is built with lateral capacitors, shown here with the proof mass displaced somewhat against these springs. This capacitor, which is smaller in distance, is actually larger in value. So this differential capacitance becomes imbalanced, the one on the top larger than the one on the bottom. Into these fixed cantilevers are fed two equal and opposite electronic signals, 180 degrees out of phase. Those signals are then demodulated or amplified somewhat, and the phase, the phase of the larger capacitor comes out, and the amplitude due to the very small displacements is linear in displacement. So this is really a displacement transducer with a mass. A proof mass is displaced against a spring and detected electronically. It's very, very sensitive. The displacement transduction of the airbag sensor is under an angstrom. It's about a half an angstrom that can be sensed. That's the equivalent displacement noise within the device. We built, again, a complete system on a chip. The block diagram is shown here, and I'll take you through some of these blocks to show you how the system actually works. The sensor is shown here, and I think I described that. There's a feature for the sensor which is self-test. Since it's capacitive with electrostatic capability, you can actually create motion with the voltages. So we can create an electrostatic self-test function that's on the sensor itself. There's an oscillator and a carrier generator that creates the signal I described on the last slide. It actually goes through a demodulator, a buffer amplifier, and there's a calibrated output at a place called VPR. That output is then fed to a final stage amplifier. That's the case because in the early days, we had 3 partners, and each of them wanted a slightly different range. So we reached an agreement where they could set the final gain. We would provide a calibrated signal, and they could deal with, amplify the output or filter it at this point as they saw fit. It also came with a standard reference building block such that the output was an absolute value of acceleration. They're shown here a block called feedback. In the first system, which I'll describe a little more fully, there's actually a closed balance force rebalance loop that essentially keeps the center member very close to its null point. The system was realized again in 1991 and shown here in the original package in which it was sold. Again, it's a complete monolithic chip. At the very center, you can see the exposed sensor, which I'll show you ever more close-up pictures of as we go on. It's in a 10-pin package, again, to accommodate the gain requirements of the variety of users. And it has something which you may or may not be able to see. It has trimmable thin film resistors. This whole chip can be calibrated at the wafer level. Looking at the block diagram a little bit, you can actually see the resistors that are trimmed a little more closely, and the fact that all of those functions described on the block diagram have actually been implemented on the chip. The sensor itself is I think, very photogenic. It's sort of made it into a lot of publications just because of its very colorful nature. These thin films are dielectrics on the order of a half wavelength of light, and they show that the tether, the sensor in actuality is 42 differential capacitance cells. Half of the proof mass is is actually in the fingers that stick out and half the proof mass in the center member. And again, this resides about 1.5 microns above the surface of the silicon. The very first device realized a sensitivity that was about 20 millivolts per G with about a 15% distribution, so that we could essentially sell everything. The distribution of sensitivity is about 1 millivolt per G standard deviation. The offset of the device is probably the hardest thing to control, and maybe I'll talk a little bit more about that later. The noise on the very first device, which has 10 to the minus 7 grams of proof mass and a fairly sensitive circuit to detect very small displacements, is in the order of 10 millig's per root hertz. The noise in the device is very white. Excuse me. The noise in the device is purely white noise, so one can make trade-offs between several kilohertz of bandwidth and more noise, or a hertz of bandwidth and a lot lower noise. Oh. From the beginning of the 80XL50, we went to several developments, customization of the package and the silicon, and also a rather dramatic improvement in the sensitivity. Finally, there was some architectural advances I'll talk about in a whole family of new devices, first spawned by a device called the 80XL76. The initial package, which was in a hermetic can, had the attributes that it's essentially welded. And so the properties of the device, which are established at room temperature in testing, were preserved very well through the process into the back end. But this device cannot be automatically assembled. Again, a feature that I'm sure many of the mechanical engineers in the audience can get involved in terms of integrated circuit automated assembly into PC boards. So dip packages, in this case an 8-pin through-hole mounted dip, and soon to come a 14-pin 14-pin surface mount device were used for the packages. So the improvements in terms of sensitivity and bandwidth were done through mostly improvements in the sensor. Some of you might have noticed that the original XL50 sensor was slightly offset. Excuse me. Was offset slightly from the center of the die. In order to, symmetry is often wise in doing stress-sensitive devices, which just about every small sensor is, multi-sensor. The device was placed in the center, and the electronics that was used is very much the same, with some minor changes. It's easier to see on the sensor itself the characteristic of some of those minor changes. Here you see a wider proof mass. This is a folded suspension which automatically stress relieves the polysilicon. And in some cases, we actually use the polysilicon as crossovers of some of the signals. So that, and the fact that the sensor was placed in the center of die were some of the improvements. But in a force rebalanced architecture, you don't need all of the fingers to sense and all of the fingers to force. At 5G full scale, we separated force and sense, again, allowing a reduction in the noise and improvement of the overall system performance. So that in the end, we produced a next generation device, which has 200 millivolts per G, 10 times the sensitivity. The offset's more tightly distributed. The sensitivity is actually quite tighter. And the noise floor is down an order of magnitude to a millig per root hertz. So you can actually sense 1,000th of a degree or under a degree of tilt in it. just you know, a brief look at the actual material. You can actually see in this SEM photograph that the polysilicon material of 2 microns in thickness is indeed suspended above the substrate. I mean, looking under one of these anchors, these are the anchors to the substrate. And there are very small, you know, stress gradients within the material, which you can see by looking at the ends of the fingers relative to the things that are fixed above the substrate. The next generation was really motivated in a very simple way by economics. The first generation device is XL75 shown here in this slide is 3 millimeters on a side. The XL76 has the dynamic range of the 75 and the 5 and is on exactly half the die area. Hence the silicon costs half as much. It has, again, many of the things learned from the 05 and has a much simpler electronic control system, enabling us to manufacture it at lower die area. It also happens to be a precursor of a CMOS architecture, which we will be using on the next generation process. This new architecture has spawned, and the surface micromachining technology capabilities have spawned a whole new family of devices shown on the next slide. It seems clear that since the sensor is on the surface, you can easily do a 2-axis device, and the 276 is a version of the 76, which actually has 2 sensors on the same die. It ends up being smaller than the original XL50 and offering a 2-axis for crash resolution, the direction of the crash. The 105 is actually something that has another factor of 3 of more sensitivity range and better specifications. 181 is a bomb fuse with integration of distance and velocity as well. 2 integrals done electronically on the chip. The 202 is designed specifically for tilting, measuring the tilt of platforms, especially toys and games. There's a single-axis version thereof. And the 310 is actually a microwatt accelerometer, which is all 3 axes measured on the same chip. So maybe getting into some of the summarization here. What we did in this is really a constraint-driven innovation, one in which you change very little from the IC line. You spend a little money. Actually, we spent very little in the first 3 or 4 years of developing the project to the point at which you really had feasibility. You create value for a customer and you get one that wants to buy it. Then you sell the process, and the process of optimization and really building a dedicated factory, which we're now engaged in, comes shortly on the heels if you're lucky. I might say that there's a philosophy, more or less, that I think is very important to recognize, and that's one of constraint-driven innovation. I was involved in the early days of CMOS when we were told by Intel that actually NMOS was the dominant technology and it would be forever. The short and sweet of it is they don't have that position anymore, but it was done. The development was done in a line without making any changes. Similarly, this MEMS development was done in an IC line without any changes and without any new equipment. It's a case to really sort of, if you want to do something innovative, but you actually want to get something done, it's good to live within the limitations and don't try to go too far until you've actually proven the point. I think that as we look forward, there are several things in surface micromachining that are important. I think we'll see CMOS being more important as a dominant signal processing technology. We certainly have a process in mind with multiple levels of polysilicon that build off what we know and yield very highly integrated microelectromechanical systems. Just as a quick overview, both visually, the next slide is a multi-project chip. We actually have MCNC signed up to broker this process in the next over the next year or two, wherein other people will be able to try this. But there are many functions that were demonstrated all on. This is on a single wafer and a single chip. For instance, accelerometers that can sense in all three directions. Angular accelerometers and resonant accelerometers with dynamic ranges of another couple of orders of magnitude. There are also angular rate sensors, which I didn't have a chance to talk about, but they're really exciting, which together with XYZ accelerometers should enable a 6 degree of freedom inertial measurement unit. There are also some signal processing elements that you can do on the chip. So finally, while we have a nice business going with a dedicated factory, there still remains quite a bit to do. I think in the area of MEMS, we're quite ahead of the game in terms of centers of excellence at Berkeley, UCLA, Caltech, Michigan, Case Western, CMU, MIT. There's several schools where people are actually getting to know about MEMS before MEMS pervade the industry, unlike the IC industry. But nevertheless, we need to develop a bigger manufacturing infrastructure, CAD infrastructure, some particulars associated with MEMS in terms of both materials and processing, as well as the whole packaging industry that now is geared to integrated circuits that we need to get geared to MEMS. And finally, testing sensors is an area where there's an awful lot of work to do. So I guess with that challenge, I'll sort of open the floor to questions.
Thank you, Rich. Now we are ready for questions from viewers and live audiences. Do we have any incoming call? I guess we'll start with the live audience questions. Can you approach the microphone in front? Please identify yourself and your affiliation.
I'm Kathy Powell with the SMTC, and I'm a mechanical engineer. Why are MEMS accelerometers replacing inertial switches in airbag applications?
Okay, well, I think that pie chart I showed a fairly rapid, as automotive systems go, displacement of one technology by another. I think the real reason, and the reason that things happen in automotive, is cost. The mechanical switches, while in manufacture for some time, costs on the order of $8 to $15 per switch. Given their response time, they need to be located remotely in the car, and at least 3 mechanical switches, often more, were part of the typical airbag system. So you started out with about $50 to $75 worth of switches. They were located remotely, requiring connectors and wiring harnesses. Accelerometers are now under a $5 item. They plug into the circuit board with a microcomputer, and just with an accelerometer and an inexpensive microcomputer, you can run an algorithm that determines what the energy in the crash and whether or not it's a crash which needs to be deployed. So it's also that kind of system. Electronic systems are also usable on multiple platforms. You don't need a customized configuration for every platform around. So the economics is on a good day, I claim that there's about $100 in cost savings on on accelerometer-based systems over switch-based systems, and some people claim it's only in the $50 range. But $50 times 40 million cars is about $200 million, which people really want to save in the automotive industry.
We have an incoming phone call with questions. Go ahead.
Yes, Dr. Payne, this is Lonnie Love from Oak Ridge National Lab. And I'm asking about the current technology you're using for the assembly of these parts. What do you do for the assembly of these things?
Okay, the assembly of an integrated circuit is usually something where, in the first case, the devices are sawed, with a diamond saw with a water spray. Needless to say, the sensitive structures on the front surface can't tolerate that. So what we do is essentially cover the surface with normal die mounting tape that has holes in it so they don't stick to the sensors. Then we cover the holes with another layer of tape. So we have two layers of tape and the wafer mounted upside down. That allows us to saw it. And then the pick and place equipment that's used in standard integrated circuit assembly typically has pins which move the device off a chuck and onto a substrate and back and forth from chuck to chuck in some cases. In those cases, needless to say, since we've located the sensor right in the middle of the die, that's where the pins are usually on those machines. We've substituted multi-pin handling systems that only touch the die out near the periphery of the die. So the die is essentially protected, sawed, and then dealt with with customized chucks such that the device is not destroyed in the process.
Okay, thank you.
Okay, so I think this is the first part of this editing workshop for I think this is Richard Penn is really pioneer, right, to develop the world first surface micro machines, the micro accelerometer using this BiCMOS process. Okay, so again, this is not the pure CMOS, BiCMOS, because this end device they have own fabrication facility for NIC. So that's it. I don't know. Do you have any question? Any question for this particular lectures? Do you have any question? I think it's important you can try to ask a question about this. Although this is very old, it's more than 20 years old, the video, but I think it's still very useful for you to understand about how you learn from basic fundamental this kind of microfabrication process to work on real design or real amends product. Do you have any question? Of course, after 20 years, now you can see this kind of method around continue to motion sensor become more and more important. Why? Not only in smartphone, why your smartphone have this is almost 6 axis of MEMS motion sensor, and also you also have some smart watches. You need to have MEMS motion sensor, right? Accelerometer, gyroscope, even for your headphone. When you say Apple have their own this kind of Apple AirPod. I don't know if you have AirPod Pro, but actually you cannot imagine, right? Even this kind of headphone also have this kind of MEMS motion sensor. What do you think? This is quite amazing, huh? So let me show you about this specification of the let me show you. If you look at the Apple's website, AirPod Pro, this headphone, and then so that even this kind of headphone has of course MEMS microphone, also have MEMS, also have this kind of motion sensor. You see, you have a dual beamforming MEMS microphone, and then inward facing microphone, dual optic sensor, MEMS detection accelerometer, and speech detection accelerometer. You see the full sensor. You see, so this is something. As I told you, in the near future, we have a lot more of this MEMS motion sensor. Okay, not only for this kind of smartphone, VR, AR, all this need this kind of sensor. Okay, MEMS motion sensor. Okay, but that's why people think we're going to have a $1 trillion business, right? Trillion sensor will be replicated, and then so that's the future. Again, do you have any question for this particular lectures? Any question you want to ask? Any question? No? If not, then of course we do have additional lecture, so that again, please try to download this ASME okay, the SME handout from our website so that it will be much more clear to see this kind of the presentation, because this video you can see is from the videotape, right? And then I digitize, but the resolution is not as good as what you see in typical like video, right? So that that's why either you try to download this thing. Okay. Again, do you have any question? If not, and then we can go to the next part of this talk. Let me see here. Oh, sorry. This we have. Let me show you. There's another top code. Let me put here. Okay. The second one we have to talk about is relate to this kind of let me say also automotive industry. Let me check.
I'm Ed Faxlanger from Charles.
See. Let me share this screen.
I'm Ed Faxlanger from Charleston, South Carolina. Mechanical engineer, basically. You mentioned that you had worked on a second chip that had 2 axes, X and Y, I assume. And then you mentioned that you had demonstrated that you could do 3 axes. I thought that was kind of strange. Could you explain on how you can get the 3rd axis when the wafers are pretty much layered? Okay, well, as you said, the 2-axis is fairly straightforward. Actually, the 2 different 2-axis devices that were shown on that family of proliferation family chart, one of them is actually 2 independent sensors. The 2 mechanical elements, one rotated 90 degrees from the other. And that's the easy way, the straightforward way to do the second. And for some applications where you want redundant channels, it has a great merit. Simpler systems can be done with a single proof mass whose X and Y movement is monitored with X and Y capacitor plates. So one blob suspended off a spring with 2 degrees of freedom, and you measure the displacement of both X and Y. The 3-axis device is actually done with one sensor, which is a 2-axis sensor, and a second proof mass, which is actually a Z-axis capacitor sensor. It has a standard capacitor that's essentially not moving, and it measures the differential capacitance based on one plate that's free to move in the Z-axis and another plate and a fixed capacitance. So it's the same kind of differential capacitance circuitry. It's just a slightly different structure that moves up and down as opposed to laterally.
Thank you, Rich.
Thank you.
I think we just have one more question. I think we just have one more question coming in. Okay, go ahead.
Okay, hello. This is Honora Rogers, and I'm with Cordis Corporation. And my question is, back in, let me see, 1990, when you just started the feasibility for this program, how many resources did you have to accomplish the full functional accelerometer within a year?
Okay, well, the project sort of started with 4 people. There were 2 senior engineers, a process and designer, and a junior engineer and a technician in the process group, actually. So the process development was the dominant activity in the early days, and it was 4 people. That expanded to a group of about a dozen people by the time we demonstrated to ourselves that we were going to need to test and at both the wafer level and package. And right now there are about it's hard to count them, but there are probably about 250 to 300 people spread out around the world involved in rapidly ramping to meet the volume requirements for this kind of device.
Okay, thank you really now this time. Okay. Our next presenter is Dr. James Gerald Monte. Please move on. Dr. Gerald Monte is a senior scientist in the Advanced Engineering Department of SSI Technology Incorporated in Janesville, Wisconsin. SSI Technologies is a supplier of sensors to the automotive industry, and his department is responsible for bringing new sensing technologies, preferably MEMS-based, into the automotive industry. Prior to joining SSI Technologies, he was an associate professor with the Institute for Manufacturing of Louisiana Tech University, where he was responsible for the design, installation, and startup of deep X-ray lithography equipment at the Center for Advanced Microstructures and Devices. He'll be speaking on the development of MEMS pressure sensors. Jim?
Thank you very much, CJ, for the very nice introduction, as well as inviting me to give this talk. As CJ said, I will be describing the case history behind the development of a pressure sensor for the automotive market that my company embarked on back in 1989. And hopefully by the end of the talk, I will have described how this product came to be. So let me outline my talk for you. All right. I think for you as an audience, it'll be important to know a little bit about the company, because unlike some of the other companies represented here, our background and the way we got into MEMS is quite different, and that may be of interest because that also leads into some of the decisions that were made from a different perspective than the previous talk. However, you'll find that we ended up with almost the same conclusions. I'll talk a little bit about how our surface micromachine pressure sensor compares to micromachine pressure sensors, how we integrated that with CMOS currently. In other words, what is the fabrication sequence of that pressure sensor, as well as how we go about doing this without having the manpower that our previous speaker has at his disposal. In other words, we don't have a fab, but yet we can still produce wafers. Then we'll talk a little bit about the back end of the process, that is the packaging, as well as some of the current performance of the die itself, as well as the packaged die. So let me begin by describing a little bit about SSI. We are by far the smallest company represented in this talk today. We are about $90 million in sales per year. We mainly supply to the automotive market. There are a couple of markets that are side markets to us, but 98% or so of our business is with the automotive sector. We're located in two places, Janesville, Wisconsin, where we produce our parts as well as perform the design. Then we have another office in Farmington Hills, Michigan, where we service our customers. And currently we have two product lines. One is a traditional sinter stainless steel components business. That is the origins of SSI, as a matter of fact. And we have the sensors business. Now, back in 1989, SSI, as it was moving toward the sensors business, looked at the automotive market to see what areas were being covered and what areas showed needs. And SSI came up with a list of possible applications where a pressure sensor could be used. This includes MAP and BAP sensors, that is manifold and barometric pressure sensors, oil pressure sensors, fuel rail pressure sensors. Brake assist was not there in 1989, but that is a new application mainly for the European market where they want to have brake by wire. Air conditioning systems, automated clutches, power steering, stored gas for some of the newer airbags where rather than using a detonating device, some people want to use a stored high pressure gas in order to activate the bag in a more gentle fashion. turbo boost for some performance monitoring of the engine, and finally tire pressure for both safety and run flat tires. So back in 1989, there were basically two types of pressure sensors being supplied to the automotive market in production. These were based on strain gauge technology and capacitive-based technology. Both of these are macro-based type sensors. That is, you can actually build these with your hands. You don't have to use photolithography to build these sensors. Both of these are still currently in use, although they are slowly being phased out in favor of some of the MEMS type sensors. At the same time, back in 1989, when SSI looked at the research being done in new sensor technology, it found that there was a lot of work being done in bulk micromachine pressure sensors, and there was some reported work on surface micromachine pressure sensors, mainly by the Lichtenberg group in Europe and Henry Guckel's group in the United States.
Uh-oh. Uh-oh. Sorry, that sounds a little problem.
Pressure sensors, as we do not have one. And you may not be able to see this in your in the screen right now, but in your notes, you should be able to see that there inside of a package, there is a pressure sensor mounted on a substrate, and the deflection of the membrane, which is on the top, determines the strain that is finally read off, and that strain determines what the output voltage will be of the, or the output voltage difference will be of the bridge. Now, incidentally, if I may stop here for a second and make an announcement, I was informed that there was a problem with the diskettes that were sent to ASME related to these transparencies. So some of you may have actually text and pictures missing from your notes. Those of you who have that can get the corrected versions from ASME headquarters in New York. I believe that the person to contact there is Ellen Lund. So if I may get back to my talk, this cartoon shows a finished bulk micromachine pressure sensing element, which was difficult to see in the previous transparency. And it basically shows that there is a cavity that can either be closed to provide a reference vacuum or pressure for the reading, a sensing membrane that deflects upon an external input, and on that membrane there are piezoresistors that read off the strain at the edges of the membrane as it deflects due to the external input. Now, in bulk micromachine pressure sensors, it is somewhat easy to also open up the substrate that is here in pink and create a differential pressure sensor. Now, our pressure sensor is a little different. It's based on surface micromachines. So let me walk you through that process. All right, in our process, we start out with an N-type silicon wafer, and we oxidize the entire surface of the wafer to be able to pattern openings. And usually after we put the oxide down, we put nitride and pattern the nitride to create the openings and create an oxidation that will define the cavity that we're going to use as a reference cavity. Then after we remove this oxide by etching, and usually this is some sort of a wet chemical H with HF, we regrow oxide. And for those of you who are not familiar with oxide, when oxide grows on silicon, it usually swells and it expands. So that as the oxide is regrown in this cavity that has been opened up, it will form this sort of geometry on the surface of the wafer. Following the regrowth of the oxide, we open anchors from the nitride and the oxide down to the substrate so that the polysilicon plate that we're going to deposit on top of that can have direct contact with a substrate. So we proceed by depositing the polysilicon and patterning the polysilicon. Once the polysilicon has been deposited, we can come back and etch out the oxide that is between the poly and the substrate. Again, HF etch shows a very high selectivity for oxide, so we can go in and clear that out without really impacting at all on the substrate and the poly that has been deposited on top. So we therefore now have a freestanding polysilicon plate that is suspended at the edges by the anchors that you see in this cartoon over here. Now, in order to seal the cavity and provide a reference vacuum, we can come back and oxidize the poly and the substrate together. As I said earlier, oxide swells when it is formed, and as it swells, it pinches off this cavity that was, or these channels that were used to etch out the oxide. And by pinching those channels off, we get a reactive seal. In other words, we can guarantee that there is no oxygen left as gas inside this cavity, and therefore we can, by some calculations, predict that the vacuum inside a cavity sealed reactively is roughly in the order of 10 to the minus 6 torr. Okay, so now that we've created our polysilicon plate and pinched off the entrance to the cavity, we can then come back now and put a dielectric film, a nitride film, between the polysilicon plate that we're going to use as a mechanical sensing element and the electrical polysilicon piezoresistor that we're going to use to read the strain from the plate. This is done by depositing a second polysilicon layer on top of the nitride, patterning the poly and doping it appropriately so we can get the piezoresistive parameters that we want to get from those structures. Finally, to finish off the sensor, we make a contact to that piezoresistor by opening up a nitride coating that we put on top of the piezoresistor and providing metal to carry the signals from the piezos off to the rest of the die circuitry. In cartoon fashion, this is what our surface micromachine pressure sensor would look like. That is, we would only have one substrate, which is a silicon wafer we began with, the cavity defined by the oxidation steps, the polysilicon plate deposited on top of the oxide, and then the polysilicon piezoresistors that were deposited on top of the polysilicon plate. Now, what I have next are some scanning electron micrographs of some of the structures that I just described to you. And if you could zoom in, please, on the picture, I'll show you some of these structures that we just saw in cartoon fashion. What you see in this picture is the polysilicon plate anchored at the edges over the cavity. There is a slight tube-like structure around the edge, which we happen to call the bird's head, mainly because of the cross-section looks like a bird's head, and you'll see that in a few transparencies from now. You see also some bumps here that are the etch channels that we use to clear out the oxide underneath the polysilicon plate. You also see the piezoresistors that we use to sense the motion of the membrane when it is subjected to different pressures. On the periphery of the membrane, you can see both the aluminum metal coming to the contact points that we opened up in the polysilicon right here and all the way around. This particular membrane is roughly 60 microns by 60 microns. This is a membrane that we would use for a 100 psi to a 150 psi type device. Here's a close-up of one of the piezoresistors that you saw on the previous picture, and it provides a better view of both the polysilicon that is part of the sensing membrane and the polysilicon that is part of the piezoresistor. In fact, you can detect that there's a different granularity because it is actually different films. You can also see, if you look closely, that there is a dielectric between the piezoresistor and the sensing element. On the mid portion of the picture and toward the bottom of the picture, you can see again this channel-like structure that is what I call the bird set earlier, as well as the contact points between the aluminum and the polyhedra. Finally, here is a cross-section of the sensing structure. And could you zoom in a little better, please? No? Okay. Thank you. You can see here on this particular SCM, the polysilicon plate, which is 2 microns thick, that here is suspended over the cavity. The cavity here in this case is 0.65 microns. You can determine or see here a structure where the oxide came up to the surface of the substrate, and that creates this funny looking structure that we tend to call the bird's beak. And because we call that the bird's beak, then this portion here we call the bird's head. Now, for those of you who are unfamiliar with the differences between surface and bulk micromachining, I have here in a cartoon fashion a comparison between a bulk micromachine sensing element and a surface micromachine sensing element like the one that I just showed you. The key point to get from this transparency is the difference in size. Basically, a surface micromachine pressure sensor for an equivalent pressure range of that of a bulk micromachine pressure sensor will be about 100 times smaller in size. And as Rich pointed out earlier, size in silicon means cost. So therefore, we can achieve substantial savings by going to surface micromachine membrane over that of a bulk micromachine membrane. Now, the catch for us, of course, at SSI is that we also like to integrate electronics along with our sensing elements. So therefore, we incur costs by doing so, but we still have this 100 factor in size. In fact, once we have included electronics with our sensing element, our die is about the same size as a regular bulk micromachine sensing element alone without the electronics. So based on all these comparisons that I've just walked through very quickly, SSI developed some comparisons between whether to go surface or bulk micromachining in terms of the pressure sensing technology. And there are some key advantages to both. I think that that was presented in the previous talk, but let me walk you through some of these as they relate to the pressure sensor that I'm describing to you here today. With surface micromachining, of course, we can get the smaller mechanical sensing elements. That's fairly clear. It's also clear that it's easier to incorporate CMOS because of the processing required in surface micromachining is compatible with CMOS, although that is perhaps arguable by some people because the polysilicon is extremely thick, 2 microns. The oxides that we grow to create the cavity are also very thick, 650 nanometers, sometimes 900 nanometers. They're fairly thick. But nevertheless, aside from those discrepancies, by and large, surface micromachining is fairly compatible with CMOS. Also, by the fact that we use reactive sealing technology to create these sensing element cavities, we know fairly accurately what the vacuum reference is in our absolute pressure sensors. In fact, for the automotive markets at least, the 10 to the minus 6 torr is practically an absolute vacuum inside those cavities. The technology, or at least the die that I'm going to show you in a few minutes, has fewer packaging wire bonds. And being that, as I told you earlier, SSI grew out of a mechanical type environment, meaning that we first sold parts that were made only with stainless steel and are migrating to MEMS, things like wire bonds worry us a little bit. So the fewer wire bonds that we need to package our parts, the happier we are in terms of reliability. So surface micromachining does offer that to us as well. There need not be any wire bond between the sensing element and the electronics. We inherently have a built-in overpressure stop because as the plate comes down during pressure excursion, the plate, as you saw in the cross-section, is much thicker than the cavity. So therefore, it can easily fill the cavity up and rest on the substrate directly. So therefore, the substrate would become the load-carrying member rather than the membrane. And that you will also see later on in some of the performance curves that are brought with me today. So this last property of surface micromachine pressure sensors leads to the fact that these pressure sensors can operate at very high pressures very easily. And I will also show some data on that as well. On the other hand, bulk micromachining offers the following advantages. That is that single crystal sensing elements have fairly predictable intrinsic stresses. That is, you know exactly what the material is, you know the crystallinity, you know the orientation of the crystal. Therefore, it's easy to make guesses as to the performance of that sensor and also model it and so forth. In surface micromachining, a lot of the properties that one needs to know ahead of time have to be monitored very carefully during the processing of the wafer, because the morphology of the wafer can vary sometimes depending on processing parameters. So that is a distinct advantage of bulk micromachining. In bulk micromachining, the way it is currently done, that is using a mechanical element and a die, electronics die separately, one can match a known good mechanical element with a known good electronic die. In surface micromachining, the way we're implementing it, we are beholden to trying to match a good mechanical element with a good electronics. And so therefore our yields are not going to be as high as using a two-die approach. And finally, bulk micromachining offers an easy way to incorporate differential pressure sensing, which at present is not easily done in surface micromachining, although there are new technologies coming online, especially some of the high aspect etch capabilities offered lately that can produce, they can yield differential sensing elements. But by and large, it's easier to do in bulk micromachining. Excuse me just a second. I'd like to move on now and show you some of the, walk you through some of the electronics very briefly so that we can get on to the die and see the performance of the die. Our sensing element is represented in this schematic by these four resistors that you see over here. I know the Wheatstone bridge that we use is slightly in a different configuration as you would normally find them in textbooks here. But what I want to point out here is simply that we do use a Wheatstone bridge, and we take that reading into a buffer amplifier. And from that buffer amplifier, we run it through a gain to produce the output that we require, that is required by our customers. In the process, we in the path between the buffer and the gain amps, we add additional resistor structures to do two things. One is to provide an offset for our die, again, according to whatever our customer desires. Second, we provide some, I'll call them that right now, dummy resistors. But these dummy resistors provide us with some temperature compensation, because then we can play some games with the doping levels of those resistors. This is an optical picture of what our typical die looks like currently. I believe that in your notes, this picture was left out of the slide, so you will not find it there. But what this shows is our current generation die, which is 100 mils by 100 mils. In the center of the die, for symmetry reasons, as Rich explained earlier, we have 4 cavities, which are very difficult to see in this particular picture. Excuse me just a second, let me try a different version of the same picture to see if you can see it better here. Could you zoom in on this? Okay. All right. So as I was saying, on the center of the die, you can find the 4 cavities that were created the way that I explained earlier. And on the sides of those, beside those cavities, you find 2 banks of thin film resistors that we can use to trim those die, trim the membranes to balance them. You find also an op amp, which is, in this case, is the buffer, an amplifier, as well as some very large resistors that we use for trimming the offset. These are, by and large, bigger than they need to be, so that we can easily reduce the size of the die. In fact, that is currently in process for the next generation pressure sensor. I would like to try to switch gears a little bit here and talk about something that is very different for us compared to the other companies, and that is that we don't have a fab to produce these die. In other words, these wafers, like the one that I have here in my hand, are not made at our facility. We don't have the capability to produce them. So we needed to go outside the company and find somebody willing to create these elements for us, as well as the electronics. This is a viable way for many companies to go. However, I would admonish that it's rather tricky. And let me tell you very briefly why I think it's tricky. And that is that, number one, you have to locate a facility that is willing to use your process or willing to develop a process along with your company. I know that for SSI, this was a very difficult thing to do. We tried a total of 3 different fabs in the early 90s, and the third one turned out to be the winner for us. The third one, if I could mention a name, is SMC Microcomponents Division in Long Island. And they had been working with us to develop both the wafer that you just saw as well as a die that I'm going to show you results on later on. And they have been very helpful in terms of working our process through their facility and helping us tailor our process to whatever equipment they happen to have. Now, we have been very lucky with them. Let me talk about some of the pitfalls that we had with the other fabs that didn't work out so well. And the first thing that I need to point out is that no matter what contracts are in place, really what determines whether or not this relationship will work is the actual relationship between the people. Sending a process outside of a company to be done elsewhere is sort of like sending a recipe for a cake to be done at your neighbor's house and trying to tell them over the phone what to do. It boils down to how well the person on the other end can interpret the data and the instructions that he or she is receiving from the customer. And relationships, for that matter, I think, for that reason, I think, are extremely important in trying to do a fabless production run. We've been very fortunate with SMC, and things I think are going great guns with them. The other pitfall that we have with other facilities is that although we were able to get good relationships with the engineers that were actually going to run the process and run the fab, the buy-in, that is the agreement to work with SSI, was not at all levels. The management perhaps was not willing to buy in, or perhaps the board of directors was not willing to buy in. And that can create a lot of problems, because even though one may have a very good relationship with the engineers may have different priorities assigned to them. The next pitfall that I would like to warn you about is checks and feedback. There are so many things that can go wrong during a process that is, if there's any doubt in the fab side that you might use the information you get from them in some negative way, you're never going to get that information. So that the feedback has to be very open for this to work correctly. And maybe you might say that this goes right back to the relationship between the fab and the engineering, but I'd like to stress it by putting it in a separate bullet here on this transparency. And finally, the other pitfall that one must always be aware of if you're going to go into production is that, will the facility be able to ramp up? We had an instance with a fab in California that could handle 20 wafers in a year, but they were not able to handle 300 wafers a month. So it's a situation where that has to be known ahead of time, I think. So how have we managed this without a fab? Aside from being able to find SMC, we have tried to develop very strong intellectual property positions for the things that we've gone after in MEMS. Not only the pressure sensor, but the other devices that we're currently working on. And intellectual property positions imply several different things. It implies being able to interact openly with universities so that you can obtain information from them, and then we can use that information to license the technologies that we think are key to whatever device we're developing at the time. For instance, in the pressure sensor, we have licensed the technology from WRF, which is the Wisconsin Alumni Research Foundation, and we have fairly good patent protection through WRF on some of the key technologies involved in that pressure sensor. Then part of our intellectual property agreement is also that we try to work very closely with universities and laboratories to develop any position that might lead to some intellectual property for the device that we're developing. Finally, on the production side, this implies that we need to have very strong ties to the fab, and we do have that currently. And we also have to be able and flexible to contract out any processes that the fab cannot carry out at the time. So this approach that SSI has taken, which is very different than the other ones you'll hear about today, and you've already heard, is that we really end up managing a project in which our wafers, by the time we get them back to our facility, have traveled quite extensively. They have traveled roughly 30,000 miles by the time we get them back. Let me talk a little bit about the packaging that we do on the die now. The packaging that leads to a device like this involves several different back-end processes. We start out with a die that I just described to you. We adhesively mount that to a glass in a glass to metal sealed package that we buy externally. Then we provide a transfer fluid medium on top of the die. This is a protection, a high dielectric protective fluid that transfers the external pressure input to the die. And then we mount all this in a plastic connector that is usually specified by the customer and a metal connector that is also specified by the customer. Once we obtain packages like that, we go through our regular testing. This is determined by the spec given to us by our customer. And to show you some of the typical results that we get, I'll provide these curves here. This curve shows the output voltage of a sensor as a function of pressure. This particular pressure sensor is 150 psi range pressure sensor. There are actually two curves that are very hard to see in this graph. One is the ideal curve given to us by the customer, where they specify the offset as well as the sensitivity they desire. The other curve, almost right on top of that, is the actual curve that we were able to obtain from our measurements. And you see a correlation coefficient on top between the two. I beg your pardon. The correlation coefficient is for the linear fit to the data that we obtain on the curve shown there. Since it's very difficult to see the difference between those curves, I have this the difference between them, what we call the error from the ideal curve, plotted here as a function of percent of the reference voltage. And what you see in this chart includes the range given to us normally in a spec, which is typically plus or minus 3.5% of free ref over the entire pressure range and over different temperatures. In this particular case, our temperatures go from minus 40 degrees C to 150 degrees C. Since we can create different membranes, we can also create different ranges of pressure sensors. I have a similar set of curves here for a 500 PSI range sensor. And you can see that in this particular plot, I have the output voltage as a function of pressure, the ideal and the actual shown together, and they're very hard to tell apart. So to see the differences, I also have this curve, which shows the difference between the actual measurement and the ideal as a function of pressure, and it's a function of temperature from minus 40 to 150 degrees C, as well as the error bars given to us as acceptable by our customers. In a nutshell, basically what I'm showing you is that the surface micromachine pressure sensor can in fact meet a lot of the requirements, or it may meet and exceeds the requirements that we currently are working under. One of the advantages I mentioned earlier about the surface micromachine pressure sensors is that the overstock protection allows us to safely go to much higher pressures. Here I show the results of a pressure sensor rated at 2,500 PSI. Again, I show the ideal, that is the customer's desired curve versus what we measure. There's a slight difference, which is amplified here in this error from the ideal as a function of the VREF over different temperatures. But again, even at this high pressure range, you can see that the pressure sensor performs within the error bounds given to us by our customer. Historically, one of the big negatives that has been said in the literature as well as by people about polysilicon membranes is that the material is very difficult to reproduce reliably, and that the material actually may fatigue or may show a significant amount of hysteresis over time. What I show here is the results, output voltage over pressure for a 500 PSI pressure sensor before and after 1 million cycles of 500 PSI. And you can see, or at least it's fairly obvious that the two curves line up almost one on top of the other. There's very little drift over 1 million cycles of operation. An additional benefit of polysilicon pressure sensor membranes is that because the cavity is so small below the pressure sensing element, if you overpressurize by accident or intentionally the membranes, they will bottom out at the bottom of the cavity without actually rupturing. In this case, I'm showing a 500 PSI pressure sensor before and after it was overpressurized 6 times its rated value of 500 PSI. In other words, 3,000 PSI. We could have gone higher, except that our testing equipment didn't allow us to go higher than 3,000 PSI. So in a nutshell, again, you can see that there's very little difference between before and after the 6 times overpressure. So in conclusions, I have shown you here that it is possible to create a surface micromachine pressure sensor with fully integrated electronics without actually having a fab. It requires a little bit of extra work, but it can be done. I've also shown you that polysilicon membranes are viable after our testing, and we continue to test them daily. And the viability, though, I have to provide this clause here, is a function of how well one understands the morphology of the poly. This has to be understood ahead of time. If not, you can run into problems. The package sensor, for us at least, it opens up a whole new market that was not available before in the automotive area. That is the pressure sensing applications between 350 PSI and 3,000 PSI, which are not currently being tackled by the old technologies, nor by the bulk micromachine pressure sensors. So finally, I just like to say that we do have parts out at customers right now being tested, and hopefully will be on platform models fairly soon. Thank you very much.
Thank you, Jim. We have probably a couple of minutes to entertain the question. Do we have any incoming call? Since we have only a couple of minutes, I will entertain one question from the live audience. And for those of you out there, you can hold on to your questions. We have extra 30 minutes at the end to recap, so you can ask questions to Jim using that time. So we'll entertain one question from this side here.
Jim, I'm Ed Faxlinger from nice East Charleston. And my background has been steam plants mostly. And I'm wondering how do these pressure sensors hold up under extreme heat and possibly radiation? Are they any better than the ones that are on the market already?
That's a fairly good question. I will have to answer that in two parts. One is that we in our applications in the automotive area, we're not going after in-cylinder pressure sensing with this technology because we know that CMOS will have a limited range in the temperature, limited application in the temperature range of up to about 280 degrees centigrade. We don't trust our CMOS beyond that particular temperature. And even at lower temperatures, you may find that the electronics will drift somewhat, so that we typically don't specify anything above 150 degrees centigrade for that reason. On the radiation side, I don't know what levels of radiation you're referring to. Obviously, we have to do EMC testing, and we've done fairly well in the EMC testing up through about 1 megahertz. Beyond that, we're working on that. That's mainly a function of the packaging that we have to provide certain protection for the die and the package itself. If you're talking about radiation in terms of alpha, beta, or gamma particles, I suspect that all bets are off in terms of this technology.
Thank you, Jim. For those of you who want to send questions through fax, you can do whenever, anytime during the talk today, even those who already passed, because we can use the 30-minute recap at the end. We will collect all those fax questions and give to the individual speakers at the end. Now we will be going to our half-hour break, which is a lunch break if you're on the East Coast, or a coffee break if you're on the West Coast, very early coffee break. And we'll be back at 10:05 p.m. Eastern Time. PM.
Okay, so again, I don't know, do you have any question for this particular lecture by the industry engineer, right, who redesigned this kind of main pressure sensor for automotive industry? As I give you additional information, right? That this is 20 years ago, the major application of main sensor is for, right? It's really for the automotive industry, right? Including main accelerometer for airbag, also this kind of pressure sensor for the engine control, right? This kind of pressure sensor really used for the engine, MAP, manifold air pressure, sensor for engine. But as I show you nowadays, I would say more and more, most likely, all the new smartphone will have this kind of pressure sensor, right? Again, but it's not for engine. It's really for some new application. This kind of pressure sensor for the smartphone is used for what? We have 3D indoor position application called LBS, location-based service. So this is something you should understand, so that now with this kind of low cost, this kind of main sensor, then you enable of a lot more application. It's not only just a traditional application. Okay, so that's something is I think very very special now. Yeah. So I don't do you have any question? Again, I upload this one ST microelectronics, the main sensor for smartphone. This is a much more compact design, right? Because again, your smartphone is very small, right? So that you don't want your packaging to sound large, right? The one in your no, the car is much bigger. Okay, let me show you about this particular thing I share here. You can open, go to Canva website and then try to look at this particular product, high resolution main sensor, which is much smaller form factor, right? Because this is, and also it's digital pressure sensor, right? And then enable 3D indoor positioning, enhance GPS in portable device including your smartphone and smartwatches and all these things. So this is, I think, a new application, I would say. Right? You see 3D positioning and GPS and portable devices. Okay, so this is something you should understand. Yeah. Of course, LBS also very special. Right? Location-based service, that means if you bring your smartphone to some the building, the shopping center, and then so they can detect, okay, you come here, and then if the shop can send some information about their product to your smartphone, and then so that this is another kind of application, which is something with smartphone, with this kind of main sensor, with kind of IoT, internet, right? So that in this case, enable of a new type of application. Okay. Yeah. Okay. Again, do you have any question for this particular application? Huh? Any question? Huh? Okay, so that if not, and of course, if there's some little break, and then I will go to another topic, right? So that here we have the number 2, and then number 3 lecture is also for automotive and automotive industry. So that let me show you this another one. So this for the fuel injection, right? Every engine, right, using the gasoline engine, you need to have this kind of way to do this kind of injection of this thing. And then let me show you this particular one.
Mechanical engineering from Seattle University. His presentation will be on the automobile fuel injection with the micro machine nozzle. Thank you.
Thank you. Good morning and good afternoon. I'm here to present kind of like a case study dealing with the silicon micro machine fuel injection nozzle, which was developed in the mid 80s, or excuse me, in the early 90s for a fuel injection application. And the purpose of this particular nozzle was to control flow with its precision, and also to improve the spray characteristics of the fuel. This talk is really going to be about the packaging aspects of this nozzle and how it was used in the automotive industry. So our silicon micro machine fuel injector is called SMM. This SMM was produced at another Ford plant. It's the injector itself at EFHD. And what we're going to do is go into the product background of this fuel injector, how both the nozzle, the silicon micro machine nozzle, and the attaching components in the assembly of the valve body were made. We're going to talk about some of the experiences in assembling and utilizing these components. We're also, there's a product summary that we'll review, and there's some future products that we'll discuss briefly. To get you familiar with the injector, I've a view of the assembly here. This is a standard fuel injector produced by EFHD, that's Electronic Fuel and Handling Division at Ford Motors. They produce this SMM nozzle, or this SMM injector. And at the very tip of this SMM injector is our silicon micromachine nozzle. You may have trouble seeing this, but the part we're mostly interested in is in this very front section. This is where the valve body assembly is, and where all the packaging of the fuel injector occurs. So you can maybe barely see the 4 holes or the 4 orifices of the nozzle. The valve body assembly consists of a valve body, a washer or a virtual surface, and a retainer. The SMM nozzle itself consists of a single piece of silicon. Let's look at this particular view first. This is a single piece of silicon. That's a single crystal, N-type. It's about 16 mils thick. There's 4 precision orifices etched in it in a single etch. We'll go over that process. The feature sizes on this might be difficult, but there's some very sharp corners on here. The feature sizes are controlled down to 70 nanometers. The SMM, this is a section view of the same nozzle, just to go over what sorts of jobs it was supposed to do. The metering orifice was supposed to control flow, but this is mostly in the high flow dynamic range of the fuel injector. So this is not in the idle section, but this may be when you're going down the freeway or something like that at a higher RPM condition on the motor. The other job it was supposed to do was supposed to control droplet sizes and improve them. And improvement means smaller droplet sizes. Typical fuel injectors of its day had 180, 200 micron particle sizes. In this case, this was down to the 120 micron particle size. The third thing, which is not shown here, but it's supposed to be deposit resistance. The intake environment of the engine is kind of a hostile environment, and basically you need to have something that resists the amount of foreign material that attaches itself to the injector. This prevents the clogging of an injector and the reduction in flow. Okay, we're going to cover the background here. The SMM injector was produced at EFHD, Electronic Fuel and Handling Division. The nozzle itself was produced at FMI, which is Ford Microelectronics and Company. That's where I work. Where the injector was used was on the 3.8 liter engine platforms for model year 94 and 95. It wasn't in every engine platform, but it was almost on all the 3.8 liter engines. Virtually 4 million nozzles sold. And then there was a specialty application that we sold to Magneti Morelli for the alcohol injector market in Brazil. And to better understand the packaging process, what we're going to do is we're going to go through the fabrication process of the SMM nozzle and then the packaging and fabrication process of the injector. The process flow for the SMM nozzle is pretty simple. It's a standard type of wet etch flow for the bulk micromachining industry. Which basically start with is a a single wafer. In our case, it was a N-type single crystal 4-inch diameter wafer. You do some photolithography on it. You do a wet etch. Ours is KOH. And then what you do is you go through a process of verifying and testing these products prior to shipping it. The verifying, which we'll go here in a second. It's kind of an arduous process that we were able to automate. First thing what we did basically was an optical inspection. We inspected both sides of this wafer after the etch. We looked, it was very easy to inspect for defects on the surface because the surface is very much mirror-like and defect-free. After the surface inspection, then what would happen is that we would go in and inspect every single orifice. We had a very high magnification inspection system, and we would basically inspect the size of each one of the orifices. These sizes were then converted into a dimension that we would graph out regularly and control on our system. If something was too large or too small, then what would happen is it would be put onto a wafer map and later would be rejected in our pick and place operation. This is a box and whiskers chart dealing with the orifice size, and it was a typical lot. It was, I believe, in the month of January of 94. Each one of these particular data sets represents one wafer lot's worth of orifice size information. And it's grouped in, basically it'd have an overall population size, and then for each section is worth about 25% of the overall lot. Off to the one side, it deals with the size of the orifice, and the specified limits of that orifice was 194.4 microns plus or minus 1 micron. And our inspection equipment had gauge capability down to 1/4 of a micron. So what we would do is that we would inspect every single orifice automatically. You'd load this machine, you would step through, you would acquire data. Those units that exceeded the specification were rejected. Our typical lot yield was on the order of 60 to 80%. So this particular lot represents about 50 wafers worth of material, and there's 400 units on a wafer at 4 nozzles per wafer, so there's an awful lot of measurements associated with that. After the wafer's been verified, then we took the system through a wafer saw operation where we cut it up, and we had to hold our dimensions very carefully. This is going to be later placed into an injector retainer, and they wanted as much precision as they can get out of our part. So they wanted to control both the pattern location of the nozzles as well as the overall size of the nozzles. Once the nozzles have been verified, then they're ready to be put into a final packaging material. This is for shipping, and this was done with a pick and place operation. It's very common in the semiconductor industry. What would happen is that you'd have to basically align. We performed a on-site inspection as it was placed in the pocket tape as well. And at this point, it was shipped to our customer in a tape and reel format. The fuel injector valve body assembly, which is where the injector nozzle was destined to go, had to interface with several parts. The assembly consisted of a retainer. We kind of point out to these parts. The retainer is the outside piece part here. Then it consisted of a stamped washer, our nozzle, and a valve body. Then finally, the valve assembly was welded together. there's like 10 different welds and perimeter weld. And then finally, we would inspect our units, both, optically with a reflective method, looking for surface flatness, as well as using infrared microscopy. Now that you kind of understand how the packaging is arranged on a fuel injector, based on the valve body, I wanted to kind of go over some of the problems that we encountered. There's both problems are things that you fix along the way, and successes are those things that you have fixed and you've continued on. So let's start with the problems, and we definitely did fix these particular problems along the way. Most of the problems dealing with our product dealt with our nozzle in the assembly, and what would happen is that you would end up cracking or breaking these nozzles. They're very easy to detect, but we wanted to get our defect rates down to a low and acceptable minimum number. The biggest contributors to the problem basically was bending stress on our nozzle, and that was induced by basically two different types of features. First one deals with the foreign material in the package assembly. And this starts with foreign material that's created into the pocket of the pocket tape that's sent to the factory, as well as foreign material that's generated during the handling operation and getting it into a valve assembly. The package components also contributed to the bending stress problem. And we're going to go into those in a little more detail here. Bending stress, which would basically put a high amount of tension on the inlet surfaces of the nozzle, and cause a crack or damage these particular nozzles. Because what would happen is in the stack of the assembly, if you get a particular particle, whether it's silicon or metal or something else, you would basically induce a moment on that particular surface, would cause high tension in these areas, and then can cause the nozzle to crack. Sources for this foreign material dealt with our wafer saw processing, and what the condition of the nozzle as it left our factory, handling damage that could happen in our pick and place operation, as well as in our saw operation. Handling damage at our EFHD plant, and we had basically some issues with the industrial environment and what their expectations were in handling this device. At FMI and in the saw process, here's a good example of something that's very, very small and cause a lot of problems. In our dice.
Okay, so I think we almost run out of time for today's lecture. So that again, you see, so the design of MEMS and fabrication of MEMS, this kind of sensor is still important thing, right? You see, for this particular MEMS pressure sensor, the packaging also important thing, right? This kind, again, mechanical stress also important for this packaging issue. So that so that's why, as I mentioned before, so that it's still challenging for all you engineer to come up with a good design of MEMS sensor and good fabrication and the packaging, right? Okay. So I don't know, do you have any question for the next lectures? Huh? Any question? Oh, I think this is something I understand. So that I would give you this kind of show this kind of YouTube lecture so that you can watch this kind of video in advance, and then next time I will give you we can discuss about something. And of course, please try to look at the SME handout from the Canvas website, so then you have more idea. Right? Of course, you see now this kind of your smartphone also has this kind of pressure sensor. Actually, it's a much more compact design, right, compared with those kind of sensor in the automotive industry. I will show you one of this STM micro pressure sensor is LPS22HP. Okay, it's kind of, this is if they say this is one of the smallest pressure sensor in the world. Okay, so that really used for the smartphone application. Right? You say in your smartphone, everything should be much more, more compact, right? So this requires as a better design, right? So that this is not show here. You can also look at more information about this. Again, your smartphone pressure sensor is also use piezo resistive tie, and then so that the special application is the pressure is really designed for the we call barometric pressure sensor, right? Barometric pressure sensor measure the pressure in the air. Okay, yeah. I think we almost run out of time. So again, so that if you have any question, please try to ask question on our campus website. So that again, I will try to for some students, if you want to review, and I will probably try to put this kind of record the video on campus website as well. Okay, I think that's it for today's lectures. Okay, bye bye. Okay.